Hello, everyone, and welcome back. We're continuing our discussion about trees by now looking at 2-3 trees. Now, a 2-3 tree is what we call a balanced tree. Balanced trees are variants of binary search trees, which means that they're kind of similar in terms of like having an order to them and that they're a tree, so they have similar kind of constraints and definitions, but they add additional restrictions to the structure to kind of avoid that worst case behavior. If you don't remember, the worst case behavior that we're talking about is when we ended up with our binary search tree looking something like this, right? We ended up with the stick. We never went in any other direction. We ended up with a height of n minus 1, where n is our number of nodes, which means that all of our operations were in big O of n, which isn't actually any better than a regular linked list. So what we're covering is 2-3 trees. I'll also make a note here that actually says we will be covering ABL trees as well. We're going to do it in a different video, but we will be covering those as well in this class. Red black trees are somewhere else, and B trees are somewhere else. There are other types of trees as well. There's also a 2-3-4 tree, and actually many others. But yeah, so balanced trees help us get rid of that worst case behavior of still staying in that big O of n space. So the definition of a 2-3 tree is defined recursively, just like our other ones, where we have either our base case, which is a single node, height 0, because there's no edges, right? And or a 2-3 tree that is of height greater than 0, has one of the following two shapes, either a root node with 2 children. So this is shape number 1, where we have this node sitting at height h. This is sitting at height h minus 1. Or a root node with 3 children, each of which is a 2-3 tree of height h minus 1. So you'll notice that two things change between these two. One is the addition of another child, right? So this is our 3 children versus 2 children. And the other thing that changed is the size of this node up here. And that's because we actually do end up storing more information in it. So when there's only 2 children, we only store a little bit of information here. And when there's 3 children, we have to store some extra information in here. So we've actually lost that binary part of our binary search tree. Now we can see that 2-3 trees don't have to be binary. They can be ternary, right? We can have up to 3 children. However, this definition does require us to stay balanced, which means if a 2-3 tree has a height h, then every single branch of the tree from root to leaf would have that same height of the same length of h. So what that more, I guess, specifically means is that we could have a tree that looks like this, like this, like this. And these are all valid 2-3 trees, but something like this is not a valid 2-3 tree because this height is not the same for all paths down. We have this one has a height of 2 in this case, and this has a height. So we have 2, we have 2, but on this side we only have 1. So they don't all from root to leaf, from the root to every leaf, have that same length of h. So this one would then be not a valid 2-3 tree. So we have to stay full and balanced for it to be a valid tree. Okay. So here we can see it's a 2-3 tree of height 3. The key factors here is that we notice that that means that we have 3 edges that go from root to leaf along every single pathway. It has nothing to do with the number of children, because we can have 2 children or we can have 3 children. So it's not that every single one has to have the same number of children. It is that every single node has either 2 or 3 children, and the height is maintained from root to leaf. So here there's 2 children, and then this sibling has 3 children. That's totally fine. We see that here as well, where this child here has 3 children, but these two have 2 children. That's okay, because we stay nice and balanced in that length. So every single node has either 2 or 3 child nodes, and every branch root to leaf is exactly 3 edges long. All right, so when it comes to defining this sort of structure in a node, we'll just very quickly jot some information down here. we have our node class. And originally, when we think, let's start binary search tree, we had a piece of data, we had a left, we had a right, and that's all we had. It was very like a small set of data, right? But now when we're going to talk 2-3 tree, this changes a little bit. Remember how I said some of these have a larger are like larger nodes? That's because a 2-3 tree node can hold more data in it. That int data becomes an int array of data that we can put in here. And instead of only having a left and right, we can have a left, a middle, or a right. And this is typically drawn as an array of node children. Like this. So every node has either 2 or 3 child nodes, and every branch is exactly 3 edges long. So this would house all of our data. This would house the pointers to each of the children. So there's a piece of data here. Data would be housed like this. And then our child array, that's supposed to say child with 3 spots. 1 pointer is there, 1 pointer is there, and 1 pointer is there. All right. So the nodes in a binary search tree can contain data that's organized or will contain data, pardon me, that's organized according to the binary search tree property, which means that if we have one of those small nodes with only one piece of data, which also will mean that we have 2 children, the child on this side, so let's make this a node class again. I feel like it's important to actually have that. So here is a node object. It's referring to this node object right here. So we have like that data array that would look something like this. And in spot D0, in spot 0 is that first piece of data. And then we'd also have that children array, like this, where each of these is null right now. There's no children in this case for this given node. Now, I will also say that, as we know, if we do have children, we will have 2 children coming off of a single value one. You can't only have 1 child. You either have 2 or 3 children. So if 1 data, then 2 children. Obviously, if it's just a root node, that's not the case. But in a tree with like actual data in it, so if 1 data and height greater than 0, we automatically know we're going to have those 2 children. And then in this case here, if 2 datas, we're going to have 3 children. And that's kind of an always known fact. So what that looks like over here for this one, it will look something like this. This is this node, oops, sorry. This is this node object. We'll have our data array with both pieces of data in here, D0 and D1. And then we'll have our children array as well. I'm just going to put the word child because I'm going to try to keep my space here. And again, in this particular scenario, these are all null, but we would assume that they would all be pointing to other node objects if our height was greater than 0. Now, when we have multiple pieces of data in these nodes, D0 is always less than D1. So it is sort of an ordered insert. The nice thing is if we have to do some kind of shifting of our data around, if we enter a D0 that ends up being bigger than D1, it's a really quick, easy shift because we only ever have 2 pieces of data. So it's really not a big deal. So we can see here that if we suppose that a node has 2 child nodes, so this is like not just a root, this is a height greater than 0 scenario. If we have 1 piece of data in here, it contains 1 value. That's it. This whole side is going to be all data that's less than this piece of data, and all of the right tree values will also be greater than this piece of data. So that actually holds true just like it did in a binary search tree. We don't have to complicate our understanding of that at all. 1 piece of data means it looks like a binary search tree, and that binary search tree property will hold. It doesn't mean that we can't have like a 3 node situation down here or down here. but we're going to look at what the 3-node situation means right here. If a node has, suppose a node has 2 pieces of data. This is 2 child nodes, but it shouldn't. It should say 3. Sorry about that. Then it contains 2 values, D0 and D1, and we know D0 will be less than D1. And what that means is that everything in the left subtree is going to be less than D0. Everything that's in the middle subtree will be greater than D0, but less than D1. And everything in the rightmost subtree will be greater than D1. So this is a 2-3 search tree. So we're keeping our data nice and organized according to the same search rules as we had before, only now we have upwards of like 3 pieces of data. So if we made, let's just go back up here for a second to this right here. No, I want to have a little bit of a bigger tree. Let's look at this one for a minute. Let me just delete all this. Okay, so if we're just going to look at this for a second and imagine none of this is here. This is just going to be too big of a tree otherwise. Just looking at what we have here, I know that this has a single piece of data in it. I know that this has 2 pieces of data in it. I'm going to actually number these like ever increasing. So this has D1 and D2. This is a data point number 3, data point 4 and data point 5, data point 6 and data point 7, data point 8 and data point 9 and data point 10. What this means is up here, data point 11 and data point 12 will live. Data point 0 is going to be less than data point 11. Data points 1 and 2 will be between these 2 values, and data point 3 will be greater than this value, which of course then means it's also greater than this value. Here we'd have just a single data point 13, which tells us that everything below this side is going to be less than this data point. So 4 and 5 are less than 13. And then these 2 data points are going to be greater than 13. We come over here, we'll end up with data point 14. What this means is data point 8 is going to be strictly less than 14, and data points 9 and 10 are going to be greater than 14. And then we can come up here, and this large node, because there's 3 children, are data points 15 and 16, which means everything on this side of my tree now, all of these are going to be less than D15. All of these are going to be between data point 15 and 16, and all of these are going to be strictly greater than data point 16. Okay. Cool. So that is how we organize our 2-3 tree data. I think I'm going to leave that video at this. And in the next video, we'll actually start breaking down the different things that we can do in a 2-3 tree. Some are relatively simple, like a search, and some are substantially more complicated. Well, medium complicated, like an insert, or substantially more complicated, like a delete. So I think I'll leave it at that with just sort of the general description of these 2-3 trees. And I'll see you in the next video where we will talk about some of the 2-3 tree operations. Thanks, everyone, and have a great rest of your day.